All right, I wanted to take a minute and create a video that was a little bit more in depth about anthropometrics and center of mass specifically as we work through this module. The reason why is because as in biomechanics, as a biomechanist, we care very much about anthropometrics and especially different body measurements because it affects how we move. And I hope to go in depth and kind of make that case a little bit more here in this video. First and foremost, I hope that this word, anthropometrics, is not too intimidating. You can kind of split it right here. Anthropo, kind of the Latin root for human being. And that may sound familiar to you, right? Think about like anthropology, if you ever took an anthropology class. And I'm not talking about the stupid store. I'm talking about, the class, which is a study, anthropo, study, human beings, ology, study of. Here, we're looking at is anthropometrics, meaning the measurements of human beings. And these can be basically anything, right? They can be mass measurements, like you record your mass or your weight. They could be height, but even more so, they can be broken down into like segmental anthropometrics, right? So, what's the length of your arm or your leg? What's the circumference of those things? Understanding how these measurements are determined and what effect they have is a pretty important part of our field. And that I think is mostly because everyone is different. You and I, we both have, well, I shouldn't speak for you. Most people have, two arms, two legs, 10 fingers, 10 toes. But what's always been interesting to me is the insane variability between people, right? No two humerus bones are the exact same. No two upper arms have the same density. No two upper arms have the same circumference. And this obviously applies to every aspect of our physical bodies. And so, because there's variation, we're not just machined objects, we're not mechanistic or as mechanical in nature as we'd like. There's a ton of variation between people, person to person, and this variation becomes even greater when you look across ages. Obviously, when you look across sexes, obviously, when you look across races or nationalities, these anthropometrics change depending on our evolution in large part. Evolution, exposure to things like foods, exposure to chemicals, exposure to hormone regulation. All these things can affect how our body grows and therefore what our anthropometric measurements are. So because everyone's different, yet we all have, at least for the assumption being we all have similar body parts. It's really important to understand how our mass is distributed on our skeletal system so that way we can consider that in the calculation of human motion. And so I put a picture um, of these trucks that are unbalanced in their load. I hope you can appreciate that um, it's important for us to understand how load is distributed around our body. Our skeleton, our skeletal system, our skeletal frame is responsible for uh, a number of things. Protection, structure is another one for place for our muscles to insert and attach on. But another one is for it to help distribute load. And if our load distribution, the way our mass is distributed across bones changes, you could appreciate that that's going to change how our body moves through space. If we have, some people are, top heavy, they have broad shoulders and big muscles. Other people are much thinner. I think of like marathon runners in this case. A marathon runner versus a football player are going to have much different distributions of mass about their frame, and that's going to impact how their body moves through space. From a biomechanics perspective, we simplify some of our assumptions as we make biomechanical models. And one of the assumptions is that as we consider our body's segments as we move through space, it doesn't make a whole lot of sense to try to model the body exactly as it is. I mean, how would you do that? How could you model or make a computer program that accounts for skin and accounts for veins and arteries? It's that's computationally taxing and burdensome. And we really don't do that. What we do, however, do is model each of our segments like a cone. And you can see here in the middle image, each of the body segments represented in different kinds of cones. And that's kind of been shown to be a good representation or good simplification in terms of what we can expect or how we can expect our body to perform from a kinematics perspective, right? From a moving through space. The shape of our limbs, the shape of our body segments kind of represent these inverted cones. And even from there, we go through and we whittle this down from a forces perspective to just straight up a stick figure and talk about how segments intertwine with each other. But what I'm really trying to get at here is this cone shape assumption that we make for our um, body segments. And this goes on in that, as you can probably think or tell, with these cones that we model, they are wider proximally and more narrow distally. But you know that again will change for every single person. Every single person has different anthropometrics. Every single person is going to have different circumferences. Everyone's going to have different distributions of mass. And so these are important considerations for us. A lot of the work that was done up until now kind of started in like the 1950s from an anthropometric measurement perspective. A lot of this work started back then and started with a guy named W.T. Dempster, Wilford Taylor, I believe. Dempster. So you may come across some of his work. He's got a pretty famous article. Maybe I'll show it to you at some point from the 1950s where he was looking at. He was working for the Navy or for the Air Force, I believe, and looking about how to fit pilots into different seated configurations. And so he really began diving into body sizes and segmental sizes so they could maximize performance in military in soldiers. Um, what they kind of have done since then is taken a number of different cadaver studies. These cadaver studies, they take um, cadavers and they cut them up. They segment out their shank, they segment out their thigh, their arm, their wrist, their hand, all the different body parts, and then they study them individually as individual body parts and not as a connected body. So they take your shank out, they hit, your shin, and they put it on a scale, and they get a measurement for the shin and a circumference and a length and a buoyancy and a density, and they take all those kind of measures. And over time, they've developed databases that have these measurements of body segments that we can use to create fairly accurate models. And now that we're in 2024, things are getting even more specific. It used to be when this started that the only anthropometric data we had was from cadavers who obviously were deceased individuals, but they were deceased of natural causes. And early studies only even included like 5 or 6 cadavers. And so you'd have these anthropometric measurements that people would then adapt to their modeling practices for their calculations. But these anthropometrics were based off of, um, you know, cadavers who, at the time of their death, were usually Caucasian, white, and old males. And so if you think about the body frame of an older individual, oftentimes we go through all kinds of um, muscle atrophy where we kind of shrink a little bit. Our skeletal social structure shrinks, um, and so it's often been held that those early studies that used older adults as cadavers may not be reflective or indicative of individuals who like for example are young healthy adults or children or women, for example. And so there's been plenty of work done to study anthropometrics across kind of all populations. So I hope you can now appreciate why we care about the study of anthropometrics and what value it brings, because it underlies all of the assumptions we make and that we're going to talk about for the rest of the semester. All of our kinematic and kinetic equations that we're going to do rely upon the idea that we have a pretty good understanding about the physical properties of the segments that will be moving through space. Now, one of the important anthropometric measurements we often calculate is segmental length, right? Segmental length. And you can get online and see kind of normalized data or normative data for different segment lengths, especially expressed as a percentage of height. right? So we know, for example, that your forearm is a certain percentage of height. And this is kind of what Dempster would publish. Forearm is, I have to look up on the table. I can show you all the table, but it's such a percentage of the overall height of the person. You do that over enough people, you can start to get pretty normative data sets. Well, nowadays in the lab, what we do is we use marker coordinate data to determine segmental lengths. And so it's very easy for you to come into the biomechanics lab, and maybe you've seen, but we put the reflective markers on you at different points on your body, specifically like bony landmark points. We might put one on your hip, on the outside of your knee, and then on your ankle, and then maybe on the end of your toe, something like that. And then from there, it's very easy for us to say, well, the distance between these markers represents the segment of our curiosity, right? And you can kind of see now how we model if we put one on the tip of your so maybe the top of the head, for example. Obviously, we'll do the other leg as well, and we can break the human body into our different segments as kind of like a stick figure. And so, using marker coordinate data is an important way that we in present day determine segmental lengths. And again, this is just kind of supplementary explanation to everything else we've been doing. In the homework for this week, you're given marker coordinates for a couple different spots of the body and asked to calculate segmental lengths. And so I wanted just to, with that understanding that I gave you, kind of walk through what I mean by this and kind of model exactly what I'd like you to do for that. And so you can see here that we have the iliac crest, the greater trochanter, the lateral epicondyle, which is the outside of your knee, the lateral malleolus, which is the outside of your ankle, your calcaneus, and your fifth metatarsal phalangeal joint. So if we were to those are the bony landmarks. Those are bony landmarks on the body where we in the lab would put those little reflective dots onto you to represent the locations um, of those bones. And so the way I like to draw this is I'm not a good artist, but consider that we're looking at somebody's left leg and think about looking at somebody from the side. You're looking at them from the side. We would clearly have somebody's pelvis right here. We would have their thigh, we'd have their like shin or shank, and we'd have their foot, right? That's clearly the side profile of a person. And what we're saying is that we're going to put a marker here on the iliac crest. We're going to put a marker here on the greater trochanter. We're going to put a marker here, right, on the lateral epicondyle, the lateral malleolus, and then on the side of your foot. To be able to then calculate those segmental lengths. Now remember though that in the lab we don't have any of these segments. All we get are these marker coordinates, and that's what's demonstrated right here. We have x and y coordinates, two-dimensional coordinates for where those markers are. And obviously because we only have one set, this is kind of a static image. And so if you were to put this on like on a Cartesian coordinate system, kind of like the figure I showed you earlier, you'd have your x-axis right here, you'd have your y-axis right here, x representing horizontal, horizontal placement in meters, and the y-axis representing vertical displacement in meters, right? And so now you can see that, for example, the iliac crest is located at 0.718 meters along the x-axis, that's an M, I promise you, and 1.065 meters vertically. And hopefully that makes sense, for the average adult. I don't know, the top of your pelvis is about a meter high, that's kind of a good benchmark, and so that seems to check out. And then you can see that we have different marker coordinates along the way. So the question then becomes in the assignment, how can you calculate segmental lengths? And I thought it'd be kind of a good idea to calculate maybe like the thigh length together real quick, so that way we can be on the same page and you can see what that looks like. So I want to remind you of a little bit of math review. If I say that we're going to define the thigh as the distance between the greater trochanter and lateral epicondyle, what I want to say is that here's my greater trochanter and here's my lateral epicondyle, okay? My greater trochanter is at 0.702x, and 0.892y. And my lateral epicondyle, the outside of my knee, is at 0.647x. Oops, it's not a variable. 647x and 0.489y. So then the question is, if we're calculating the length of the segment, we first need to make a segment, right? And I hope you can appreciate that all you have to do is just draw a line between those two and you get the segment. I kind of drew like a not straight line because, there we go, through that number right there. But that's my thigh segment that's connected between those two dots. But how do we actually determine that length? Well, basically what we can do is, if you're not picked up on it yet, my favorite shape in the world is a triangle. And anytime we can make a right triangle, we can use trigonometry to determine pretty much anything. And I love doing it. So my first suggestion here is to kind of sketch out a right triangle here. We know it's a right triangle, so it's going to have a right angle right there. Well, we know that, if you have A, B, and side C, if we know that side A is simply the distance between our x coordinates of both of our markers, we can simply find the length by subtracting the two x coordinates. And so we can do something along, if A, well, that was weird. A is going to be equal to, x1 minus x2. Or, in other words, x of the greater trochanter, can I just put GT, minus x of the lateral epicondyle, right? And if we subtract, 0.702 from 0.647, that'll give us this length right here, right? The distance in between those two things. And so erase, erase, erase. We come down here, we say 0.702 minus 0.647, right? And we can calculate that the length of side A is 0.055 meters, okay? And obviously, when we do length of side B, we're going to do the same thing. This time it's the difference in our y coordinates. And so B will be equal to y1 minus y2, or y proximal minus y distal, right? B will be equal to 0.892 minus 0.489. So the length of side B, 0.403 meters, okay? Well, now we have a triangle. I'm going to erase these A's and B's and say that this is 0.403 and this is 0.055 meters, okay? And now all we need to do is the quick Pythagorean theorem to determine the length of side C. And so we can say that A squared plus B squared equals C squared. And we know that A was 0.055 meters squared plus 0.403 meters squared will be equal to C squared, such that C, when we take the square root of all that, will be equal to the square root of 0.055 meters squared plus 0.403 meters squared. And if we crunch all those numbers, we calculate that C will be equal to 0.4067, that's a 4 meters. We can round that up to like 0.41 meters as the length, right? As the length of our thigh. Good. I hope that was helpful and giving you a little bit of opportunity to think through how to calculate segmental lengths for the lab assignment. All right.